First, I would like to thank the organizers for inviting me to speak here. It's a great pleasure. Thank you. I'm going to talk about rate distortion theory for mixed states, and this is a joint work with my collaborators in University of Waterloo, Debbie Leung and Kodai Kroiba. So first, I think it's a good idea to talk and explain simply what is rate distortion theory about. So if you look at these two pictures, the one on the left is the original image, and the one on the right has almost 85% less information. So this one is the distorted version of this original image, but still, if you don't zoom in too much, you are going to be able to distinguish. Like, you're going to say, this is a picture from mountains. Rate distortion theory, we have data in quantum rate distortion theory. We have some quantum data, and we have a mathematical way of defining and characterizing the amount of error and distortion. And the main question in rate distortion theory is that given some amount of distortion, what is the minimal amount of information that we need to keep in our data? And so the whole rate distortion theory is about characterizing this trade-off curve between the minimum amount of information that we need to keep and the distortion. So I thought maybe the audience is very general. Maybe I review some very basic mathematics of quantum information. We know that if we have many quantum particles, we can define a state of all these particles together with a density matrix on a tensor product Hilbert space. So let's imagine that we have some quantum data, and it's going through some process, how we can mathematically model all these processes is with a completely positive trace preserving map, which maps any input state to output states, and the output states also describe quantum particles. And also, you're familiar with the notion of fidelity. So the fidelity, if it's equal to 1 between two states, it means that they are exactly the same, and it's 0, it means that they are orthogonal. So for mixed state, the fidelity is defined like this. Okay, then let's talk about quantum data and quantum data compression. Quantum data compression was initiated by Schumacher in 1995, and basically he generalized the notion of statistical quantum, the statistical classical data defined by Shannon to the quantum case, and studied the optimal compression limits for this quantum data set. He defined a quantum source as an ensemble of pure states. Let's imagine that we have a quantum source that emits in IID copies from these sets, like each of these states is coming from this ensemble with some probability distribution, and assuming these IID copies is, of course, a very big simplification, but it's the first step to understand this problem. So Schumacher defined the source as NIID copies. So let's imagine that we have input sequence of data. So the compression is about applying a CPTP map with the encoder, which is a CPTP map, and mapping it to another quantum system, which has a smaller dimension because we are trying to get rid of a lot of information and minimize the data. But of course, we want to be able to recover the original data, but we cannot recover the original data perfectly because a lot of information is lost during encoding process. We want this output sequence to be as close as possible to the input sequence, and there are some measures, for example, fidelity, to talk about figure of merit of this task. So the one that Schumacher, for example, considered is 1 minus average fidelity is the error or the distortion for this compression scheme, and the main theorem that Schumacher proved was that the optimal compression limit is equal to von Neumann entropy of this average ensemble source. So before talking about rate distortion, I would like to mention a peculiar behavior in the I said that we can define the error or distortion for the output states, but if we look at the fidelity between the whole input sequence and the output sequence, there is a very interesting behavior in the error. So if we go a little bit below the optimal compression rate, which is the von Neumann entropy of the source, then the error suddenly jumps to 1. So it's like that we can never have trade-off because of this particular behavior, and this is called a strong converse behavior, which was proven by Josa and Schumacher, and for assuming that the decoder has a unitary structure, and later generalized to the most generalized case, assuming that the decoder can be any CP-TP map by Winter. So this particular behavior, strong converse, holds if we consider the fidelity between the whole input sequence and the output sequence. But we can also consider some looser error criteria or distortion. So let's imagine that instead of comparing the whole input sequence with the output, we do it locally, symbol-wise, like the first qubit with the first qubit, the second with the second, and so on. This is called local error, and in information theory, it's very well known that if we have local error, we can have trade-off between the compression rate and the distortion. And the aim is that to characterize this rate distortion theory curve. What I was trying to say, that depending on how you define the distortion or the error, you can have different kind of behaviors. So rate distortion theory is very well understood in classical information theory, and in the quantum setting also is extensively studied for pure states. One of the initial works, as far as I know, is from Data, Hesche, and Wilte from 2012. So they characterize a rate distortion curve for ensemble of purified states. So maybe you would like to know, okay, if this is studied for pure states, what are the challenges that we are facing if we consider the mixed state scenario? So I would like to say, okay, one of the main or basic techniques that we use when we are dealing with pure states is the decoupling phenomena. So that's coming from monogamy of entanglement. So imagine that we have some entangled state, pure entangled state. By monogamy of entanglement, we know that this state cannot be entangled with the rest of the world. So it is decoupled from everything else. So since in source compression, we want to recover the data approximately, then this output state is going to be almost pure. So it's going to mean that it is almost decoupled from everything else in the world. But this is not the case for mixed states. If we have a mixed state, it can still be correlated or entangled with other systems. And therefore, the techniques that we are using to deal with pure states in data compression usually do not work in the mixed state scenario. So I'm gonna formally say our problem statement. So let's imagine that we have this ensemble of mixed states. That's the rate distortion theory for mixed states. So there is a reference system that stores this X value, and the whole time we want to preserve the correlations with. In this work, we generalize the rate distortion theory by assuming that the encoder has some side information system, some extra system that's going to help us to compress more. So if this decoder can see the index of this X, it can see the X, it is called the visible scenario, and if the side information system is just a trivial system, then it's going to be the blind compression scenario. So we are considering this general compression model, and this C can be anything, but I explained two extreme cases, the blind and visible compression case. And also, we assume that entanglement and the encoder and decoder could have shared entangled between them. So if they have access to this extra resource, of course, they are going to have perform better. They're going to be able to compress more. And as for the distortion measure, for example, Schumacher defined a fidelity or trace distance, but we consider that distortion function is any function. The only constraint is that we assume that it is a continuous and convex function of quantum states, each of these input copies of the states. And we try to find a minimal compression rate for a given amount of distortion. So this is a general thing. It's not that we only consider fidelity or trace distance. Okay, so maybe it's if you are not that much familiar with information theory, I mean in the sense of Shannon, there are two kind of directions in the proofs. So one direction is the achievability proof. In the achievability, in the task I said that we have the encoder and decoder, right? So in the achievability proofs, what we do is that we explicitly construct this encoder and decoder that achieves a certain amount of compression for a given amount of distortion, or sometimes if we don't care, we mathematically show that there exists such encoder and decoder that can achieve a certain compression rate for a given amount of distortion. This is called achievability proof. What we do in our setting is that we use already existing protocols such as quantum state redistribution and Schumacher compression, and we modify these techniques to apply in our scenario to show the existence of such encoder and decoder. And the other direction is proving the optimality of the rate. So how we are interested to show that we cannot go below that optimal compression rate, and this is called the converse proof. So basically converse proof is about saying that for a given amount of distortion, for any encoding and decoding operation, your rate is always lower bounded by something, and this is called converse proof. So to do converse proofs, we usually use some properties of entanglement measures, for example, monotonicity of entanglement measures on the CPTP maps, and then we usually deal with information quantities of the whole sequences together, but then computing this kind of stuff is very difficult, so we are interested in single-letterizing this kind of quantities, which means that we want to get rid of n in the sequence and lower bounded by a quantity that doesn't depend on n, and that's how we can simply compute this stuff. So one of our main theorems is proving the optimal compression rate in the entanglement-assisted case. Entanglement-assisted case is the scenario that we assume the encoder and decoder share free entanglement, how much they want to need, they're going to consume it. I don't want to explain too much about this formula here, but I'm going to point out that this rate distortion theory, which is the minimization over some kind of CPTP maps that minimizes this mutual information quantity here, such that the distortion that is defined like this is a convex continuous function, is smaller than d. And this rate distortion function doesn't depend on n. So it doesn't depend on the whole sequence. And the statistics of one of the copies in the sequence determine this function. So basically it is very easy to understand. And also if we want to compute this function and characterize it exactly, we can do this optimization. And the other theorem, the main theorem that we have in the paper, is about the unassisted case, when encoder and decoder do not have access to free entanglement. In this case, our rate is in terms of some entanglement measure, which is called entanglement of purification, and I thought maybe review in case you don't know what is that about. So imagine that we have a bipartite state, rho AB. We do a purification with system R, which purifies system A and B, and we apply a CP-TP map on system R to get a new system E, and then we look at the von Neumann entropy of A and R, the new system E together, and we are interested in minimizing the von Neumann entropy for these two systems, and that is called entanglement of purification. So one of the main open questions in quantum information is that it's still not known this quantity is additive or not, even though there are some suggestions that saying that this is not additive. But unlike something like minimum output entropy that's known for a while, that it is not additive, this is not known if this quantity is additive or not. So when we don't have any access to free entanglement, the rate distortion function that we obtained is this crazy formula here. So it depends on the whole sequence of data. It's entanglement of purification, first of all, which is not known to be additive or not. That's one difficulty. The other thing is that the minimization is over CP-TP maps that depends on the whole sequence of data. So in general, it's like that we have found a closed form formula, yes, but then it's also kind of useless if we want to talk it, if we look at it from practical perspective, because this is an unbounded optimization, and we don't know how to compute these kind of functions. Okay. I said that in the entanglement-assisted case, we have this nice formula which depends on the mutual information. We know how to compute it. But in the unassisted case, we have this crazy formula. But there are some special cases that we are able to compute this kind of formulas. And one of them is that we had this side information system C that is extra information fed to the encoder. And if this side information system C is a trivial system, it's just nothing, then it's called blind case. We are able to show that this complicated rate function is a von Neumann entropy of two subsystems in a specific formulation of the source. So it's, in this case, it's going to be easy to compute this one. Actually, this is not something that we prove directly in our paper. This is an implication from already existing compressions for mixed states from Kouachi and Emoto, but we show that in the limit of very small distortion, our rate converges to this one. So we operationally prove this formula, but we don't know how to do it like using entropic inequalities. So what we do in the paper is we show that this function is equal to the von Neumann entropy of some subsystems in the Kouachi-Emoto decomposition. This maybe doesn't, I don't want to talk so much about this decomposition here. I'm just saying that this is a von Neumann entropy and it's a single letter. It's easy to compute, and that's the main maybe point about this equation here. Okay, so I don't want to talk so much before the coffee break. Maybe I can conclude something here. The main point in our rate distortion theory paper is that first of all, we unified the blind and visible compression models that existed already in the literature. Unlike the rate distortion theory for pure states that was already studied, the blind and visible model were not distinguished. So this other important thing in our result is that we don't have any specific distortion measure. We consider distortion to be any function that is acting on quantum states, but the only requirement is that this function is a convex function and it's continuous with respect to quantum states. So I explained that when we have free entanglement shared between encoder and the decoder, which is called entanglement-assisted case, we are able to characterize the rate distortion function. It has a very nice formula. It's a single letter. It doesn't depend on n. It's easy to compute. In the unassisted case, we had this complicated formula, which is a function of entanglement or purification, and also depends on the whole sequence of information. We don't know how to characterize this one. There is something also called full rate region, where we find the trade-off between the amount of qubits that we need to set and the amount of entanglement that's consumed in this setup, and we characterize this in the paper fully and find the trade-off between the entanglement rate consumption and qubit rate consumption. I would like to say, like, what are the main open questions in rate distortion theory and these compression problems is understanding how to single letterize, for example, find sub-additivity or super-additivity for entanglement measures and this kind of properties, specifically for entanglement or purification. It's known for a while, but we still don't know if it is additive or not, and it would be great if we have more understanding, because this entanglement measure appears in some other communication tasks and quantifies some other resources consumed in these tasks. So it's very important to understand the properties of entanglement or purification. And with that, I would like to conclude. Thank you.
Well, thanks very much for the interesting talk. Are there any questions? Here? Is there where are the microphone cubes?
Right.
Excellent talk. Thanks. So can you give me a little bit of physical idea of what the implications would be if this rate was additive or was not?
Sorry, can you repeat? I didn't hear very well.
So you're questioning whether or not this rate is additive.
Uh-huh.
Can you give me some physical implications of if it is versus if it is not?
Uh-huh. So if it is additive, then if it is additive, then this is gonna be some of the terms, and then each term we can compute, and then the whole entanglement of purification is gonna be k times this entanglement of purification. So if it is additive, we can completely characterize the function. But if it is not additive, then basically these kind of things that appear as the amount of resource consumed is an unbounded optimization. So we cannot compute this one. It's like we have obtained some rate, but we don't know how to deal with that. So most likely it's not additive, but even if it is additive, if it is additive, then it's going to be very easy to compute these functions. So that's, I don't know if it answers your question, but from physical perspective, I don't know, like from computational perspective, maybe I answered like this one.
Do you have any intuition on why it is not additive, in example 9?
So I have done some calculation that shows that this kind of resembles minimum output entropy. And the minimum output entropy, it's already known that it's not additive. I have some hints from there, but also there are some numerical simulations that suggesting it's not additive, but these numerical suggestions could have errors. But also entanglement of purification operationally characterizes some tasks rate, which is similar, quite similar to entanglement of formations that appear in a similar task. So most likely, I mean, I'm just saying, but probably it's not additive. Sure.
Thanks for the very nice talk. I have a question about the way at the beginning you quantify the distortion, so between the initial quantum state and the final one. So you use for the volume entropy for the whole system, and after for individual qubit. And could we imagine that we would take the
two-side reduced density matrix and then take the von Neumann entropy to keep more track of the correlation.
So you're asking about the local and global error, but what is the role of von Neumann entropy there?
At the beginning, you were taking the von Neumann entropy for the part with what is called, if I understand, the loser error. Yeah, exactly. So first you take the von Neumann entropy of the whole state, and after you take qubit per qubit, if I understand well.
So the von Neumann entropy is actually the rate, this one, but this error is characterized by fidelity. So the von Neumann entropy is not related in this case, but the distortion is like we define the fidelity symbol-wise, that's called local, or we define it globally, and that's called global error. But von Neumann entropy is the one that appears here in the rate.
Can we imagine that we take something like in between local and global? Like two-side reduced density matrix, and then we apply the fidelity?
So there is something else that it is, like we have this local error, and actually in the paper we consider a bit more complicated version, and that's average. We do the averaging over the local errors for the whole sequence. That's one thing that we had done, but other than that, I don't know how to characterize something in between.
Okay, thank you.
Sure.
Okay, any last question? If not, then let's thank the speaker again for the very nice talk.